Hey guys, what's up? Eddie Aho here with KissAnalog.com. Alright, so I just did a video that I posted kind of introducing the Spectrum Analyzer, kind of showing how to take your first measurement. Now, Spectrum Analyzer being different than an oscilloscope, right? It has a spectrum of frequencies versus decibels. And I kind of showed you how you set up the scope, kind of how it works a little differently than a scope. And yeah, so what I want to do is just do a real quick video today using the PicoScope. The PicoScope's pretty unique. It has a way where, like my GWN stick up there, it can do, it's called an MDO, mixed domain, okay? This PicoScope's called an MSO, mixed signal, meaning it goes from time domain, scopes type stuff, to logic analyzer, okay? So it kind of does two different domains. The MDO does two different domains. It does an oscilloscope, time-based, and it does like FFT, like a spectrum. It's supposed to be more like a spectrum analyzer than an FFT. Now, the thing is, it's not really a spectrum analyzer, even though it kind of looks like it. Okay, kind of looks and feels like a spectrum. Like on this thing, when you set up your frequencies you want to look at, there's two different ways. You can say, I want to start here, I want to end here, start and stop. Or, which a lot of people use, is they'll say my center frequency is going to be here, and my span is going to be this. So my center frequency could be the 10 megahertz clock, like I have coming in here, and my span is going to be 12 megahertz. So it'll be 1 megahertz on this side of it and 1 megahertz on this side. I could just say it's going to start at 9 and end at 11. So same, just two different ways to do it, right? The thing is the reason spectrums use that center and span is because a lot of times that's what you're thinking. You're like, oh, I want to look at this frequency, but I want to look at these side bands. I want to look at the frequency, this many frequencies before and this many frequencies after. So I want to look at the span. And it's kind of like in an oscilloscope frame of thinking where you go, oh, I want to look at this and then I want to zoom in and zoom out, like on a touchscreen. You can pinch and pull it, kind of like on my mixed sig back here, okay? So, spectrum. So that's why this one they call it a spectrum, because it looks and feels like a spectrum, even though it's still scanning like it does like an oscilloscope, and it's taking all that math, doing an FFT on it, and then it just allows you to set it up like a spectrum. A spectrum is different because it's like kind of like a radio with somebody tuning in frequencies all the way across. It has this little bandwidth filter that you just scan across here and you pick up different frequencies. So that's a little bit different. Now, it doesn't really do it that way. That's the way you kind of think of it. It really sets up a filter, whatever width, the bandwidth of that filter, and then it sends a signal through it, and then it draws it up on the screen. So it's kind of the same, it's essentially has this spectrum and it puts a filter across. You can think of it that way. I don't know if that makes sense. We're going to talk more about this. I don't want to get too much into the weeds on this. So I just want to do a quick video kind of showing you how the PicoScope, I can show the two windows at a time, because like what I started saying, it's unique because unlike that scope, and even though it's an MSO, it really is a lot like the spectrum. It's very flexible. And one of the really unique things is I can put a scope window up and I can put a spectrum window up side by side, top and bottom, however I want to configure them on my computer screen, okay? I can also pull up lots of windows. They call them windows. I can look at a window for channel 1 through channel 4. I can look at the spectrum through 1 through 4, so I can have 8 windows up if I wanted. So I'm just going to come over, stop talking, and just show you, okay? Because I just thought it'd be a real quick, easy way in case, you're still trying to melt this into your mind. If it's first time you've seen one of these things, I get it, you know. And FFTs are something that a lot of people don't use just because, you know, the understanding of like what exactly it's doing. Okay, so I just thought this PicoScope is a great instrument where I can show it to you side by side. So let me stop talking and I'll show you. All right, guys, so here it is. You see the two windows on the bottom. See this tab right here in the middle? It says scope. So on the bottom, I have my scope waveform. And look at this. It's time-based, 0.4 microseconds, 0.2. So I've got 0.2 microseconds per division. Up here at the top left, it says 200 nanoseconds, which is 0.2 microseconds, right? The other thing I want to point out up here, see samples up here says 1 kilosamples. Just pay attention to that as we, you know, I'll point that out a little bit later, okay? But up here, just to familiarize yourself, you with the Pico, is it shows the time base here, my trigger here in the middle, and then it has some other stuff. You don't have to worry about this waveforms. It just captures like 10 screens. I can go back and look through them. I could change that to more or less. And over here I have hardware resolution. Now most scopes are 8-bit, like that GWN stack up there, but so I can change this to 8 bits. And you see how it changes this window down here? So that's 8 bits, but I can, well, I'll leave it for 8 bits for right now. So over here on the left, I have channel A through C, or well, I have channel A through D, but I'm only using channel A, so the other channels are turned off. Here's my digital stuff. Those are all turned off. And here's my generator. It's set at 10 meg, 1 volt. So if I come down here at the bottom of the screen and look at the scope window, I can see this 0 to 1, 0 to -1. I'm not using the full screen here. I could, you know, zoom in on that if I wanted, but this is good enough for what we're doing. And you see it ringing a little bit. That's probably because that 10 meg, the impedance mismatch. So it's causing a little bit of problem there. No biggie. So what I want to show you is up here, the top window, see up here it says Spectrum. And that's the window that's actually highlighted. That's, yeah, see, I can highlight these windows this way. Okay, so anyway, this window up here is highlighted. Over here you see the 10 meg clock, then 20. These are the harmonics after here. So you see how they kind of drop down as you go on? Well, they're also kind of wide. There's not a lot of resolution there, right? So what I want to do is I want to increase my samples so I get more samples, do more math, and it's kind of like changing the bandwidth on the spectrum. And what I do is in the scope mode, I spread it out a little bit. I get more cycles, okay? So see how I just went to 500 nanoseconds per division? And I've got a lot more cycles down here, and this got narrower, and I went to 5K samples. So now I go to 10K samples. So see, now it's starting to look pretty spiky. I got pretty good resolution, and so it's looking pretty good. Now, the other thing is, this is kind of like the ground floor down here, the grass, the weeds, whatever you want to call it. And we're close to, I don't know, this is like between 51 and 64 dBs. I could get curses out measured, but we don't really need to go to that detail. I just want to point out that 64.5 dB is this line right here. Now watch what happens when I come up here and I go 10 bits. Look at that. It's got this bits up here is the vertical resolution from top to bottom. How many, it's kind of like how many millivolts or microvolts I can read between here and here. So I get a little bit more detail in the math, and it pushes this down, so it's pushed it down a little bit. But now if I go a little bit more, see, now it's worse, right? But look over here, 1.25K samples. So see, now if I go back to 12, I go back to my 5K. And if I go to 8, I get 10K. So it's kind of a trade-off. But I think I can go to 12 bits, and I think that's a good trade-off. I think I'm actually getting some pretty good resolution. So with this scope, you have a lot of flexibility. You can change your vertical resolution, but you'll change. What happens is it takes away some of the bandwidth. And since we're looking at a 10 meg clock, that's why we're seeing this. If I was looking at a 1 kilohertz clock, or 10 kilohertz or something like that, I probably wouldn't even see that. I could go to 14 bits and get great resolution. But as it is, that's what's happening, okay? Now I could probably make up for it by getting more cycles like that. See, now I'm back to 10K. So let's say if I can go to 25K. Now see how it's pushed this noise floor down? Now let's see if I can go up in bits again. See, it kind of went back up and this dropped down to 6. Let's see if I get more cycles. So eventually there's a point of diminishing returns. You might be noticing maybe I'm losing a little bit of my actual frequency resolution here, so maybe that's not working as great. Yeah, see that 10 meg? It pretty much disappeared when I did that, right? Look at that. Well, actually what it did is it shifted it over. See over here, we're at 60 megahertz, so I'm losing my frequency resolution. And now right there, I still got my 200K, and so right there, it's maybe, so anyway, you have a lot of things. So I'm kind of bragging, kind of showing about the PicoScope. I just think it's an awesome scope, but yeah, so there you go. I can go back to 8 bits, and with all those cycles, I'm getting pretty good noise floor too. And here's the peaks. So there you go. I just want to point out that we have frequency across here and decibels right here. So these are dBs, and I can change the kind of dBs, like dB millivolts or whatever along here. But this is measuring decibels because decibels helps you look at very small things and very big things in the same picture, right? And across here's frequency, where down here I got time and volts up here. So that's the main difference, is I'm just looking at a whole bunch of different frequencies. Guys, if you're looking, at a waveform on your scope, you can zoom in and see some ripple on top of your, let's say you got a 1 kilohertz, or let's say you're talking about that 10 megahertz clock and you see that ringing on it. You could zoom in on that, but that's not really telling you about the harmonics, right? So it's hard to see that stuff that's happening at multiples of the frequency you're looking at. You can see things like artifacts of other things that, like if you've got a FET that's ringing or something, you can see that 10 megahertz overshoot ringing. And on this thing, besides the harmonics from the 10 meg, I could also see little peaks in between, and that's coming from that ringing. So I could look at that frequency and find it on the spectrum as well. So that's the difference between, hopefully the Pico made it a little bit easier, and maybe it also was helpful to see the difference between a spectrum and a scope and an FFT. So we're going to come over here, look at the spectrum again, and so you get one more glance at it before we start looking at some more interesting type signals, okay? This is just more in-depth introduction to get a better feel for this, so you don't get lost when we start looking at other stuff. And we're just not talking about, the setup and what you're looking at, okay? So let me bring the camera over. We'll take a closer look at this thing. All right, guys, so here we are looking at the spectrum again, okay? Here's the frequency button that we use a lot. This is kind of like how we'd use a horizontal button on our scope, okay? So we use a frequency and span and center. So the center is 50 megahertz right here in the middle, and span is 100 megahertz. So it's touchscreen as well. So we can go 50 and then megahertz. And by the way, this is a really nice touchscreen. I've liked this. It's not too sensitive. It seems to work just the way a touchscreen is supposed to work. So really like it. So, but we can also set it up as start and stop. So see, stop is 100 meg, and it says start is 0. Now really, Spectrum Analyzer starts at 9 kilohertz. If you guys know why they start at 9, it's funny they don't start at 10. I always wonder why they didn't start at something that sets up, on the logarithmic graph. But I always just assumed it was because by 10 kilohertz you want it to be flat. so they run down to 9, so that between 10 and it's kind of funny, it goes to 2.1 gigahertz. Like, why not just go to 2 gigahertz or 1 gigahertz for that matter? But going to that extra 2 gigahertz, you know, that extra gigahertz is meaningful. And I guess that 0.1 was important too. And that's the other difference between a Spectrum and your FFT, is you can go way out to this, you know, these gigahertz frequencies, okay? Now, our noise floor, by the way, is down here minus 40, 38. Not super impressive, but that's because we got big wide pulses here. If we come back over here, amplitude, let me just finish this up because the frequencies cross here. Okay, so the frequencies right here, the span is 100 meg and 50 meg is here. But see this resolution bandwidth, 1 megahertz. So we're only looking at 1 megahertz bandwidth. That's not, you know, that awesome, right? So instead of kilosamples and stuff like that, like the digital scope, it's talking frequencies. Now, what we can do is come over here. Well, you know, the other thing is amplitude, right? Up here, our scale is 10 dB, so 10 dB per division. Where over on the scope would be 1 volt per division or 1 millivolt per division, something like that. So that's your log scale. And right now we're set at 10. And I just hit this amplitude, and up here it says 20, 22. I'm going to put 20. Now, the way you set up this, again, I talked about this in my other video, but just cover that again. Usually on a Spectrum, the highest signal you want pretty close to the top line. That way you can use that whole screen. You try to get the peak of your signal up here, and then try to get the noise floor down here at the bottom. Where like on the scope, you'd probably have the 0 reference down here, and you try to get your, you know, your voltage going up here, or if it's AC, you get in the middle, and you try to use your whole screen, right? So a little bit difference on how you set them up. Now the bandwidth, that is that resolution bandwidth. See right here, it's 1 meg. So I could go just down arrow on it, and it just goes to the next thing, 300K. And you see how the noise floor just pushed down, and we're getting down under 50. Here's 60. So we're already getting pretty good noise floor, right? And I can go down again, and see how it's pushing it down again. And look how these are getting skinnier. So that's how this is. Now there's 30K. Now look at the noise floor. It's way down here. So that's more than my 14 bits on the digital scope. So you can see how this can really get down. And look at this, 10K. So this is minus 70 dBs over here. I think 10K is no, I can go to 3K, okay? And I can go to 1K. Look at that. We're getting right off the screen, minus 80. Let's keep on going down. What's going to happen is, see how slow it starts to go? Okay, now let's change our amplitude, since our top signal is up here, but we're pushing off the screen. So then we go to our amplitude, and it's like change our volts per division, but we're changing decibels. So let's change our scale to 20. And we'll change 20 dB. So yeah, we're way up there. So we could change it to something in between 10 or 20. Usually I stick to the middle one, you know, the even 10s, but you can see 100 dB right here, 120. I mean, this is kind of like that speedometer in your car that goes up to 160 miles an hour or whatever you have that you're never going to get to, right? But here, let's go to resolution bandwidth again. And I'll push this down again. And we're going to go down to 10. Whoa, look at that, 3 hertz. That's going to take forever. So that's going to take a long time. So I'm going to come back up. And 100, I think, is going to take a little bit of time, but not crazy. You can see it moving across the screen slowly. But look how low we're getting. We're getting down to minus 80 dB. So you can imagine, if we're patient, how far down we could go. Also, if there's a particular frequency, we could go center frequency, the frequency of interest, and the span. We could change our span. Instead of going 100 meg, maybe we only go 20 meg or 10 meg. And then we could change our bandwidth down to a much higher resolution and not have to wait so long. But anyway, this just kind of give you an idea of the difference of how you set up a spectrum and what it can do in regards to what a scope can do. You would have to have a wide bandwidth oscilloscope. You know, probably cost, it'd be very expensive. It costs more than this Uni-T Spectrum to be able to get something that could duplicate this. But this PicoScope does a really fine job. It's just can't go to the 2 gigahertz, and it, can't quite give you this kind of noise floor. Now, again, you can focus on certain frequencies and probably get something really good, but yeah, just wanted to kind of get you a little bit more introduction to the spectrum and how it works and how you can play around with it and get the measurements you might want to get. So again, over here we have our 10 megahertz, and then we have our harmonics at each one of these guys, and I could go to my peak detect right there. There's 10 megahertz, 6.72 dBs. You can see that, and I could measure all those things. I can go to my peak table if you just want to see that, and it shows you the table and the values of all those. Those numbers are associated with the numbers in these columns, and then the frequency in the dBs. Super powerful for this kind of work. Alright guys, I hope that helped make more sense of the spectrum, and maybe even on how to use FFT in the scope. So maybe that helped. Let me know. Let me know in the comments. If you know why a lot of scopes or spectrums start at 9K, let me know that too. Now, I know one thing: if you get a spectrum that can go down to low frequencies, they're pretty expensive. Now, a lot of times, well, at least sometimes, they'll go low frequency, but maybe not real high frequencies. And, obviously, the Uni-T, they have one that goes to a higher frequency. It just costs a little bit more money. You can go higher and higher, and they can cost as much as, well, my house. They get very expensive. More than my house, actually. I mean, so can oscilloscopes, for that matter. But anyways, yeah, Pico has some scopes that cost 15 grand or more. So they have some expensive scopes too. Nowhere near as much as, the big name guys, but then again, you get a lot more for your value. Alright guys, hope this helped. Let me know in the comments what you thought, and if you have some ideas. I do want to show some power supply stuff and some audio stuff with this, and I do want to show some side-by-side spectrum things, the capabilities of the FFTs, like on the GW and on the MixSig even, and on the Pico, and even on the Signet. So I just want to show some of the measurements we take on those and compare them to a spectrum, what you can get on the spectrum. So if you have some specific measurements you'd like to see a comparison of, let me know. Alright? Don't know how long I have this, so I'm just going to do a few videos right now. Hopefully I'll mix up doing some power supply stuff, some audio stuff to make it interesting to see some of those things, as well as what we can do with the spectrum if you're interested in learning on how to use that. So I'll stop talking and I'll get off this. And by the way guys, I want to thank you again for all the really awesome comments and all the stuff you left on my other videos. I'm plugging away because I really do want to respond to those, and I've gone through a pretty good sized list right now, but there's still a big list left. So really appreciate that. Really appreciate you guys that have signed up on my Patreon. That's amazing. And for you guys that have hit that super thank you button, so much appreciated. And a follow-up on the insurance thing with the tree damage, deck damage, and the wall damage. Not sure how that's working out yet. Still trying to figure that out. At least they're covering the tree removal, so that's good, because wait for this, it's pretty scary. It's right around $20,000 to remove those trees. So, but repairing the deck, replacing the trees, it doesn't look like they're even going to do that, which I thought they were. I thought that was part of the trees and shrubbery. Anyway, just follow up on that. So I'm still kind of trying to figure that out and get my wall repair the, yeah, I don't think what they offered to, it's hard to get contractors out to give you bids. So, and it's been so snowy here in Utah. We've had a ton of snow, which we really need because all the lakes are drying up, if you've heard about that. And if you're in other countries, heard about how the western U.S. is just dried up, and some of our major lakes have dried up. I mean, looking really bad last year. So there's some interesting videos on YouTube about Lake Powell, and they're finding, I mean, it's kind of gross. They're finding bodies, but they're finding boats and all kinds of things at the bottom of these lakes that have been there for a long time. So, yeah, it's like Mother Nature decided to give us all that water back in 1 year. I don't know if we're going to get it all back. I think in California, I hear some of the lakes are filled up. Oh, going on a rant. Sorry. But, yeah, thanks for hanging in there and watching. Thanks for all your support. Appreciate it all. And we'll see you next time, guys. Let me know in your comments below what you'd like to see. Okay? Thank you. Hey, and by the way, it's my birthday in a few days. Ay, ay, ay. So, yeah, so it's going to be a busy weekend with Easter and birthday. So, happy Easter to everybody, and happy birthday to any of you guys that have April birthdays or March birthdays for that matter. Alright guys, thanks a lot for watching, and I'm going to get off this time. So we'll see you next time.